Introduction. Students, today I am going to take a surprise quiz. So you have 10 minutes to go through your chapters. And if anyone has any doubt, please ask. Teacher, can I ask you one question? Yes, ask. I have one question in my mind. We know many formulas now, like to calculate area of triangle, rectangle, circle, etc. Can we use the same formulas to find the area enclosed by curves? That is a very good question. No, we cannot use same formulas. For that, we need to study some applications of integrals, or we should go through some concepts of calculus. Well, let's do one thing. I will take the quiz tomorrow. Let me tell you about some of the applications of integrals. Objectives. At the end of this lesson, you'll be able to find area under simple curves, understand working rule for finding the area, find area between two curves, area under simple curves. Let f of x be a continuous function in AB. Then, the area bound by the curve y equals f of x, x-axis, and lines x is equal to a and x is equal to b is given by the formula a is equal to modulus of integral from a to b of f of x with respect to x, provided f of x is greater than or equal to 0 or f of x less than or equal to 0 for each x belongs to a, b. The area bounded by x is equal to f of y, the y-axis, and the lines y is equal to c and y equals d is given by a is equal to modulus of integral from c to d of f of y with respect to y. Provided f of y is greater than 0 or f of y is less than 0 for each y belongs to C, D. Working rule for finding the area. If the curve lies completely above the x-axis, then the area is positive, but when it lies completely below the x-axis, then the area is negative. However, we have the convention to consider the magnitude only. If the curve lies on both the sides of the x-axis, that is, above the x-axis as well as below the x-axis, then calculate both areas separately and add their moduli to get the total area. In general, if the curve y is equal to f of x crosses the x-axis n times when x varies from a to b, then the areas between y is equal to f of x, the x-axis, and the lines x is equal to a and x is equal to b is given by a equals modulus of a1 plus modulus of a2 up to modulus of an. If the curve is symmetrical about the x-axis or the y-axis or both, then calculate the area of one symmetrical part and multiply it by the number of symmetrical parts to get the whole area. Example first. Find the area of the region bound by the curve y square equals x and the lines x is equal to 1, x is equal to 4 and the x-axis. Solution. The area of the region bound by the curve y square is equal to x, the lines x is equal to 1 and x equals 4 and the x-axis is the area ABCD. Area of ABCD is equal to integral from 1 to 4 of y with respect to x. By solving it, we get area of ABCD is equal to 14 upon 3 square units. Example second. Example. Find the area of the region bound by the ellipse x square upon 16 plus y square upon 9 equals 1. Solution. The given equation of the ellipse is x square upon 16 plus y square upon 9 is equal to 1. It can be observed that the ellipse is symmetrical about x-axis and y-axis. Therefore, area bound by ellipse is equal to 4 into area of OAB. Area of OAB equals integral from 0 to 4 of y with respect to x. By solving it, we get area of OAB equals 3 pi. Therefore, area bound by the ellipse is equal to 4 into 3 pi equals 12 pi square units. Example third. Find the area of the region bound by the parabola y is equal to x square and y is equal to modulus of x. Solution. The given figure shows the area bound by the parabola x square is equal to y and the line y is equal to modulus of x. The given area is symmetrical about y-axis. Therefore, area OACO is equal to area ODBO. The point of intersection of parabola x square is equal to y and line y is equal to x is A1, 1. Area of OACO is equal to area of triangle OAB minus area OBACO. Therefore, area of triangle OAB equals 1 upon 2 into OB into AB, equal to 1 upon 2 into 1 equals 1 upon 2. Area of OBACO is equal to integral from 0 to 1 of y with respect to x is equal to integral from 0 to 1 of x square with respect to x. By solving, we get area of OBACO is equal to 1 upon 3. It implies area of OACO is equal to area of triangle OAB minus area of OBACO, which equals 1 upon 2 minus 1 upon 3, which equals 1 upon 6. Therefore, required area is equal to 2 into 1 upon 6 equals 1 upon 3 square units. Area between two curves. The area under a curve and above the x-axis can be computed by the definite integral. If we have two curves, y equals f of x and y equals g of x, such that f of x is greater than g of x, then the area between them bound by the horizontal lines x is equal to a and x is equal to b is area equals integral from a to b of f of x minus g of x with respect to x. To remember this formula, we write area is equal to integral from a to b of top minus bottom with respect to x. If f of x is greater than or equal to g of x in a, c, and f of x is less than or equal to g of x in c, b, a is less than c, is less than b, then area is equal to integral from a to c of f of x minus g of x with respect to x plus integral from c to b of g of x minus f of x with respect to x. Example first. Find the area of the region bound by the curves y equals x square plus 2, y equals x equals 0, and x equals 3. Solution. The area bound by the curves y equals x square plus 2, y equals x equals 0, and x equals 3 is represented by the shaded area OCBAO as shown in this figure. Then, area of OCBAO is equal to area of ODBAO minus area of ODCO. Integral from 0 to 3 of x square plus 2 with respect to x minus integral from 0 to 3 of x with respect to x. By solving, we get 21 upon 2 square units. Example second. Using integration, find the area of the triangular region whose sides have the equations y equals 2x plus 1, y equals 3x plus 1, and x equals 4. Solution. The equations of sides of the triangle are y equals 2x plus 1, y equals 3x plus 1, and x equals 4. On solving these equations, we obtain the vertices of triangle A0, 1, B4, 13, and C4, 9. It can be observed that area of triangle ACB equals area of OLBAO minus area of OLCAO. Integral from 0 to 4 of 3x plus 1 with respect to x minus integral from 0 to 4 of 2x plus 1 with respect to x. By solving, we get area of triangle ACB equals to 8 square units. Did you know? The origin of the integral calculus goes back to the early period of development of mathematics, and it is related to the method of exhaustion developed by the mathematicians of ancient Greece. This method arose in the solution of problems on calculating areas of plane figures, surface areas, and volumes of solid bodies, etc. In this sense, the method of exhaustion can be regarded as an early method of integration. The greatest development of method of exhaustion in early period was obtained in the works of Exodus 440 BC and Archimedes 300 BC. Summary. Let us summarize what we have learned. The area of the region bound by the curve y equals f of x, x-axis, and the lines x equals a and x equals b, where b is greater than a, is given by the formula area is equal to integral from a to b of y with respect to x equals integral from a to b of f of x with respect to x. The area of the region bound by the curve x is equal to phi of y, y-axis, and the lines y equals c, y equals d is given by the formula area is equal to integral from c to d of x with respect to y equals integral from c to d of phi of y with respect to y. The area of the region enclosed between two curves y is equal to f of x, y equals g of x, and the lines x is equal to a, x equals b is given by the formula given below. If f of x is greater than or equal to g of x in a, c, and f of x is less than or equal to g of x in c, b, a is less than c is less than b, then area can be formulated as